In this video, we're going to talk about general curvilinear systems. We'll talk about coordinates, basis vectors, and scale factors. So this is our overview slide, which we'll spend about 5 minutes on, and then we'll go over each topic in more detail and with more examples. We will start with general curvilinear systems, which have orthonormal but not necessarily consistent basis vectors. Examples include the cylindrical and spherical systems we had investigated in our previous two videos, the toroidal, the hyperbolic, and an elliptical systems, which we have not looked at. I have this general drawing here. We have a point P, and its coordinates are q1, q2, q3, and then we have the basis vectors at this point P as q1 hat, q2 hat, and q3 hat. And note that the basis vectors are drawn emanating from the point P, since the basis vectors will change as we move around in the three-dimensional space. We will talk about conversions from Cartesian coordinates, and we'll use our spherical coordinate system as an example. And then the next thing we will do is we will come up with equations, general equations for general curvilinear systems of our basis vectors in terms of our regular Cartesian coordinate system. That's it for our overview, so we'll start with curvilinear systems and our coordinates and basis vectors. So in general, our curvilinear systems will be orthonormal. They'll have orthonormal bases, but the bases are not necessarily consistent, so they may change as we move throughout the space, as we saw with our cylindrical and spherical coordinate systems. As you recall, in our last videos with cylindrical and spherical coordinates, we saw the basis vectors were not fixed. As the point moved, as we moved the point P around, or as we moved throughout the space and chose different values for P, the directions of the basis vectors changed. And we obtained the direction for each of the unit vectors by increasing the associated coordinate and watching how P moves. And doing that, we kind of argued, or I argued, that the basis vectors were orthogonal to each other and formed an orthonormal basis. And so that was our last conclusion. So in this video, I did not tell you how to express these bases in terms of the Cartesian coordinates, and I also did not definitively prove they were orthonormal. And so that's what we're going to take a look at here. So we're going to start by looking at the coordinates and the basis vectors of a general curvilinear system. So this applies not just to spherical and cylindrical, but in general. We will be using the spherical coordinate system as an example. So for our general curvilinear system, our coordinates will be designated or notated with a q1, q2, q3. Our Cartesian coordinates are usually x1, x2, and x3. We'll have a corresponding basis for our curvilinear system as q1 hat, q2 hat, and q3 hat. We can have formulas that convert from our curvilinear system to regular Cartesian coordinates. So for our Cartesian coordinate, x sub I will be a function of our q1, q2, q3. Remember, those are the coordinates in our curvilinear system for I equal 1 to 3. In general, for Cartesian coordinates, x1 will be our x coordinate, x2 is our y coordinate, and x3 is our z coordinate. We also can have a function that gives us our q sub I basis vector from our curvilinear system, and it'll be a function of x1, x2, x3 from our Cartesian system. Using spherical coordinates as an example, so our q1 will be r, our q2 is going to be phi, and q3 will be theta. So our phi goes between 0 and 2 pi, our theta goes between 0 and pi. So our conversion from spherical to Cartesian, we have our x1, which is our x coordinate, x2, which is y, and x3 is equal to our z coordinate. So x is a function of r, phi and theta, and it's equal to r sine theta cosine phi. Y is also a function of r, theta, and phi, and it's equal to r sine theta sine phi. And z is also a function of r, phi, and theta. Although phi is not used, it's r cosine of theta. looking at this notation here, so x1, that's our x-coordinate, is a function of q1, q2, q3. That is r, phi, and theta. And then we have our formula. x2 is a function of q1, q2, q3. That's r, phi, and theta. And we have our formula. And finally, x3, that's our z-coordinate, is a function of our r, phi, and theta. And it's equal to r cosine theta. We also have this formula here, these formulas here, to give us q1, that's r, q2, which is phi, and q3, which is theta. And it's a function of our x1, x2, x3, or x, y, and z, as you can see. Here we are on our overview slide. We just finished talking about these Cartesian conversions. And the next thing we want to do is to get equations for our basis vector for our curvilinear system in terms of our Cartesian coordinates. As we've noted, the expression for our q sub I basis vector can be constructed by increasing q sub I and watching how the position vector changes and then normalizing. So this is it. This is our formula. So our basis vector is looking at how our position vector changes as we move in the direction of our basis of our q sub I coordinate, and h of I here, this is not a term to be summed over, so this is kind of deceiving because it looks like we have two indices and sum over, but this is not what this I is. This is not what this index is. This is just to say that h of I is a scaling factor for q sub I. It's what we use to normalize. So r is our position vector, and we're going to say that it's our jth. Now this is the I here. So x1 is the x-coordinate, x2 is the y-coordinate, x3 is the z-coordinate, and this is the corresponding bases for x, y, and z, and then our q1, q2, q3. And we didn't want to use I here because we're going to use our I over here to designate which coordinate we are in our curvilinear system. And then we have dr, dqi is the partial derivative of our x sub j coordinate with respect to our ith coordinate. So this x sub j coordinate is from our formula, our conversion formula, and this dqi, this is the ith component or coordinate. And then we multiply it times our direction vector, and as I said, h of I is normalizing. It's what we divide by the length of dr dqi. So we'll do an example just so you can get a feel for these formulas. I cleared out some space, but I did keep my formulas from my spherical coordinate system because we're going to use that as our example. And I kept my equation for our basis vectors for our curvilinear bases. And we are going to start by calculating the basis vector for the r direction in spherical coordinates. And we're going to express this basis in terms of our Cartesian coordinate system. Our first example will be to compute the r basis vector for our spherical coordinates, and we're going to do this in terms of our Cartesian coordinates. And the first thing we need to do is write out r. I have some notes on that over here. So our r, according to this formula, is xj, q1, q2, q3, ej. So these two j's, the xj and the ej, this implies a summation. So in other words, our r is going to be our x1 and our e1 with our q1, q2, q3, x2 and e2 with q1, q2, and q3, and x3 with E3 with Q1, Q2, Q3. So we've summed over J at this point. Then the next thing to remember, in Cartesian coordinates, x1 is our x-coordinate, x2 is our y-coordinate, and x3 is our z-coordinate. And then finally, the Q1, Q2, Q3, that comes from our curvilinear system. That's our r phi theta. So finally, our r vector is equal to x of r phi theta in the x direction, y of r phi theta in the y direction, and z of r phi theta in the z direction. plugging this in then, so our vector r is x of r phi theta. That's written right over here. So that's our r sine theta cosine phi in the x direction. Then our y of r phi theta is right here. R sine theta sine phi in the y direction. And finally, our z of r phi theta, which is r cosine theta in the z direction. Next, we need dr dq sub I. For the basis vector e to the r, I is equal to 1, because that will give us our first coordinate here. So dr dqi, we're going to set I equal to 1 because we're looking at the r basis vector, which is the first coordinate in our spherical coordinates. So our formula here is dx sub j, q1, q2, q3, dr, e sub j, and I just got that from here. So now we have the j, which we need to expand with the summation. So we have dx1. Remember, that's just our x coordinate, so I'm just going to write x for now. Our q1, q2, q3, dr in the x direction. For x2, that's our y direction. So dy, q1, q2, q3, dr, e to the y. And then for for j equals 3, we have dz, q1, q2, q3, dr in the z direction. Remember, q1, q2, q3, that's r, phi, and theta. So let's go ahead and do our dr. And I move those notes over here. So our dr, position vector with respect to our variable, our coordinate r. So partial derivative of our x with respect to r is going to be sine theta cosine theta. Partial derivative now of our y with respect to r is going to be sine theta sine phi in the y direction, and then partial derivative of z with respect to r. So that's just cosine theta in the z direction. And then the last thing I need to compute is my h of I, which is our scaling factor, which is simply the length or the magnitude of our dir dq sub I. So in this case, our h is the magnitude of this last vector here that we computed. So it's going to be sine squared cosine squared phi, our sine squared theta sine squared phi, plus cosine squared theta. And when we add all this together, we get square root of 1, which is equal to 1. And finally now, what we have is our basis vector in the r direction now is our dr over here divided by h of r, but it's just divided by 1. So it's the same thing. The cosine theta cosine phi in the x direction plus sine theta sine phi in the y direction plus cosine theta in the z direction. And this here should be a plus, not a comma. And now what we've computed is the direction of our r basis vector in terms of our Cartesian coordinates x, y, and z. And you'll notice that the basis vectors will change according to our thetas and our phis. I can do a similar calculation for our phi basis vector. So our position vector remains the same. It's our, what is it? Where is this? Our x sub j, e sub j, and then we put in our q1, q2, q3. So here's our x here in the x direction. Here's our y in the y direction, z in the z direction. So it's the same r we used previously. Now for the phi, we want to do dr d phi now. So the partial derivative with respect to phi is our, this will take our cosine and make it negative sine. So we have minus r sine theta sine phi in the x direction. Here this will just become cosine theta, so we have r sine theta cosine phi in the y direction. And here there's no phi, so this is just 0 in the z direction. To find the length of this vector here, we have r squared, and I kind of took it out, my minus sine squared phi. I guess because of the square, this becomes positive. And here I square this. I already took out my r squared here, so I have sine squared theta, cosine squared phi, and then 0 squared. so these two, I still have my r. I should put in my parentheses here. And then I'll have my sine squared and cosine squared becomes 1, so I'm left with sine squared, but under the square root, I have r sine theta. And now to get my basis vector in the phi direction, I have my dr d theta divided by r sine theta. So here I cancel out this r sine theta and I'm left with minus sine phi in the x direction. Over here we cancel out with this and we're left with cosine phi in the y direction and 0 in the z direction. And you'll notice this basis vector also changes as phi changes. Here I have the calculation for the theta basis vector. I'll just let you take a look and verify that it's what you would calculate on your own. I will leave calculating the theta basis vector up to you, but one thing I did want to do is show that we're approaching an orthonormal basis. And the reason why I say approaching is because I haven't calculated the theta basis vector. But if we just take a look at our r and our phi basis vector, if I dot the r basis vector with itself, you can check my dot producting, I'll get a 1, which is good. If I dotted the phi basis vector with itself, I also get a 1. When I dot the r basis vector with the phi basis vector, you see I get a 0, and that's what we expect for an orthonormal basis. Here are the coordinates for the cylindrical system, so I'm going to do the same thing. I'm going to calculate the unit basis vector for rho, phi, and z. So here I have my position vector, that's my x, my rho cosine phi in the x direction, my rho sine phi in the y direction, and my z in the z direction. And I calculate next my dr dqi. So dr, and in this case, first I'm going to start with rho. So the derivative with respect to rho for each of these is going to be cosine phi, sine phi, and here 0. There's no element of phi here. So the magnitude of this dr d phi, so that I can get my h of I, is square root of cosine squared phi sine squared phi plus 0 squared. So that's equal to 1, which means my basis vector in the rho direction is simply cosine phi in the x direction, sine phi in the y direction, and 0 in the z direction. To get my basis vector for the z, now I'm going to take dr dz. So the partial derivative with respect to z here, there's no z coordinate, so it's 0. This is also 0. And here I get 1. So the length of this dr dz is 1, which means my basis vector is simply this dr dz divided by 1, which is 0, 0, and then 1 in the z direction. I cleared out my work for the basis vector for z so that I could do the work for phi. So dr d phi over here with respect to phi is minus rho sine phi. Here I'll get rho cosine phi, and here I'll get 0. So the magnitude of this dr d phi is equal to rho squared sine squared phi plus cosine squared phi plus 0 squared, which is simply equal to rho. So I divide my dr d phi by my h of I, my scale factor. So I'll get minus sine phi e to the x plus cosine phi e to the y plus 0 e to the z. The next thing I wanted to do was look at my scaling factor, my h of I over here. And remember, this is what we did to make our basis vector unit length. But you notice that for r and also for z, our scaling factor is 1, so we didn't have to do anything. It was with phi that we had to change and divide by p to make our basis vector unit length. I'm going to move this scaling factor here just to give us some more space, and we're going to take a closer look at this. The idea is this. So rho and z are already in terms of distance. So if I talk about traveling in rho, in the direction of rho, and I change my p so I'm just one more unit rho out, then the change in my r vector is in the rho direction by 1 unit. Similarly, if I'm over here at point P and I travel 1 unit in the z direction, then the change in my z direction is 1 unit. Every 1 unit change gives me 1 unit. That's what this kind of h of I says. Here, however, every change in phi, well, that gives us a change in rho. And the reason why this is different is because phi is not expressed in terms of distance, it's expressed in terms of an angle. So if I'm out here on this circle at P, and I change phi by 1 unit, one small little amount, how much I actually change my position of my vector depends on how far out, what my radius is, what my rho is, right? Because here, everything in this kind of V shape all represents phi, the angle phi. However, if I'm out here at this radius, you can see that my position has moved by a much greater than distance than if I'm at this radius. My position vector, my vector p has only changed by this green distance. And that's the thing about curvilinear systems, that when you change some of these variables, these angle variables, so in spherical it'll be phi and theta, but here when you change this phi a small amount, you're changing the distance by a variable amount depending on, in this case, depending on rho. And I've written this idea here. A small change in phi will give a different change in length of how far your point P has changed depending on rho, the radius. And we could have calculated h of I, our scale factor, by observing that the distance that our point P is moved when we move phi a small amount is the arc length. This would just be the arc length, which is the angle phi times the radius of the circle, rho. So again, the change over here is our arc length, which is d phi, the angle, the change in the phi, times the radius rho. And if phi is just 1 unit of change, then that means dr d phi is equal to rho, which is exactly what we had calculated over here for our scale factor. So that's kind of what the scale factor is doing. It's measuring how much your point changes for a 1 unit length change of each of these variables. And now we can see how that relates to our displacement vector, dr. That means our displacement vector, now if we move a little bit in the direction of q1, q2, or q3, or some combination, linear combination thereof, is equal to our small change in the q1, q2, or q3 direction times our scaling factor, and then times our basis vector, our direction vector. So expanding this out for 3 dimensions, that's dq1 h1 in the q1 direction, dq2 h2 in the 2 direction, and dq3 h3 in the 3rd direction. Applying this to cylindrical coordinates, here I have my my h1 for rho, z, and phi. That would mean that would be dq rho in the rho direction, dq phi times rho in the phi direction, and dqz in the z direction. So remember, because phi is this angle, then how the distance that we change p is going to be dependent on rho. So we have to put this scaling factor in. Your book explains this, that when you consider hi, the scaling factor that makes the curvilinear basis unit length, it has a physical interpretation, that is, for a change dqi of the coordinate q sub I, the position vector changes by a distance of dqi times hi. So just what we had discussed before. So for cylindrical coordinates, if you move 1 unit in the direction of q1, you move 1 unit for rho. Similarly, 1 unit in the q3 direction is 1 unit in the z direction. And for q2, that was the more complicated one, but it is you have to multiply your scaling factor multiplied by rho. And then we had already done all the work for the spherical coordinates, so our scaling factors, we had our h1 our HR is equal to 1, which shouldn't be a surprise because remember, R is already measured in distance, so every 1 unit displacement in R should equal 1 unit displacement in P, and our point P. Our H of phi is equal to R sine theta, and then theta, kind of what we expect from our work with the cylindrical coordinates, is equal to R. And the last thing I'm going to say on this topic, if you recognize you multiply your scaling factor and you're going to get this R squared sine theta. And you might recognize that from when we did triple integrals for volume integrals when we were talking about Gauss's theorem. And one thing I have to apologize to you for is I was using rho for R, and I switched my phi and theta because I'm a math major. And this is what spherical coordinates look like to a math major, which is like, yeah, there's a rho instead of an R. And as I said, the phi and the theta, you just swap symbols, which honestly, when I first, anyway, never mind. So the point is that when we had done those volume integrals, when we changed from Cartesian to spherical coordinates, we had, because we were integrating over a small piece of volume, now our volume is going to change in spherical coordinates because of the curvature, because of this theta, because of this phi. So we had to multiply by this R squared sine theta. But now you know where that Jacobian comes from and why it's there. And you'll see it again because we'll have another section in the book about volume integrals as well as other integrals. To review what we have covered in this video, we talked about general curvilinear system. We said that their bases are orthonormal but not necessarily consistent. And our examples were the cylindrical and spherical systems, which we have covered in the last couple of videos, the toroidal and the hyperbolic and elliptical, which we have not covered. We talked about how we could have coordinates and bases vectors, and we used the notation Q1, Q2, Q3 to notate the coordinates of our curvilinear system, and Q1 hat, Q2, Q3 hat to notate the bases of our curvilinear system. Usually for our Cartesian, we would have x1, x2, x3, and x1 hat, x2 hat, x3 hat. And then we said we could find different functions to move us back and forth between Cartesian and our curvilinear system. So if we're going to Cartesian coordinates, it would be x of I is a function of our q1, q2, q3. And if we're going from Cartesian to our curvilinear system, then q sub I is a function of x1, x2, x3. And then we used spherical coordinates as an example. And we have here going from spherical to Cartesian, we have x1, formulas for x1, x2, which is y, and x3, which is z. And then we also have formulas going the other way. For q1, that's r, q2, that's phi, and q3, that's theta, in terms of x, y, and z. And then finally, probably the most important thing or the new thing we did here, is we figured out the bases vector for q sub I. And let's see, we said that we construct that by increasing qi and watching how the position vector changes and then normalizing. So what we did is we moved qi, so we looked at dr dqi, and then we normalized with the scaling factor h of I. Remember, h of I is actually, this is just noting the scaling factor for the ith coordinate. So this isn't supposed to be summed over anything. And then in general, what we would do is r hat was x of j, q1, q2, q3 in the j direction. And then we took the partial derivative of r with respect to a q sub I. So if we wanted to compute the bases vector for the second coordinate, we would take dr dq2. So we took the partial derivative, and then we divided by its length, and we got the equation for the bases vector. The last topic we covered was taking a closer look at that HI scale factor, which is what tells us for different coordinates or coordinates that aren't naturally measured as a distance, how we would then use this so that we can interpret the change in the position vector based on changes in our qi, in our coordinate. And we said that the displacement vector then is our displacement in each direction qi times the scaling factor here. And that will become more important as we try to do integration, because we'll need to be able to integrate over small lengths. And so we'll see more of this displacement vector and this scaling factor in upcoming videos. But that's it for this video. Thank you for watching.